We're on. Don't say any bad words. Normally, just before I start the recording, I would say the list of bad words you're not allowed to say, but it's too late. I missed it. All right, well, for the sake of posterity, for the recording, that's professional face on. Welcome to the Planet Working Group. I have the great honour of leading this working group despite having a notable lack of expertise in this topic. I do, however, have quite a lot of expertise in what we've actually interpreted the exoplanet opportunity from Interstellar Probe to be, which is actually using our solar system planets as analogues for exoplanets. So as they observe their exoplanets with their single spectra and or even single pixels, we can look at our own solar system in exactly the same context as long as we have a far enough baseline to look back at it with. So that's kind of what we're focusing on. So before I get into it, I'm going to somewhat of a recap of what I think we've heard this week. I'm sure I'm showing the right one, hang on. No, that's not it. Right. Are you seeing a screen with exoplanet interstellar probe possibilities for exoplanet exploration?
We are not, Abby. Sorry.
Darn it. How about now?
It says that you're sharing screen, so maybe if we just wait a moment. There it is.
You're going to make a computer whiz kid of me yet. By the time missions are, all these missions are over. I thought I'd be there by the end of Cassini, to be honest, but no. All right, so quick introduction. So the Interstellar Probe 101. So Interstellar Probe is primarily a heliophysics type mission. Its goal is to get beyond our solar system and look back. So I hope that most of you are familiar with the IBEX and the Cassini observations of the extremes of our solar system and ENAs. So I'd love it. We could, the only habitable astrosphere that we know. I think Meredith, Ofer, and Elena had coined those terms, and I love that. So the idea is our mission gets as quickly as we can out of the solar system, so that some of us are still alive when it gets there, to something like 1000 AU. Look back at the solar system, observe our bubble from far out, and actually look at the interaction between the solar wind, the expanding solar wind's bubble, and the interstellar medium. So we're designing for a mission for the lifetime of over 50 years. It needs to be able to operate with limited power. So I think the baseline we heard from Jim Kinnison is for 2 RTGs. The launch vehicle is assuming an SLS Block 2 with at least a Centaur upper stage. The launch readiness window, I think, is from 2030 to 2040. And the examples that Wayne Schley showed you this week are assuming a 2040 launch. So I think perhaps like a worst case scenario. Which makes sense. So there are a few different notional operation scenarios. The one that we have in our grubby little paws right now is the helio version. The helio version, as you might imagine, has heliophysics-oriented payload. It's also, crucially and complicatedly for our conversation, it's a spinning spacecraft. It's going to remain spinning throughout the entire cruise phase out to hundreds of AU. The next scenario, which is, we were waiting for Christmas, but it didn't come before this workshop, is we're just starting a study where it's spin stabilized with, and so the thing that was limiting the spinning with the helio and the payload that we've currently got is that the RPWS are wires, so they can't be on a non-spinning spacecraft. They need the centrifugal force to stay out. So we're looking at redesigning the RPWS and maybe adding something like 50 kilograms for a planetary augmented payload. So we could just wait for that moment, or we could proceed and see how we can get on with the helio payload and how we might augment the currently defined mission in order to address some of our exoplanetary/solar system goals. So hopefully some of you joined Kirby yesterday. He was talking about the opportunities for KBO flybys and how we might observe small objects with the Interstellar Probe. Those are far easier because they're everywhere. No matter what direction the Interstellar Probe goes out in, we're going to be able to fly past those sort of objects. Now, as we discussed last year, the direction of the flyby is crucial for obviously to actually fly by any of the solar system planets. So I was advocating a direction that might have been something like perpendicular to the nose of the heliosphere, that maybe would have got us a Neptune flyby. Uranus is already too far over on the backside of the solar system for any of the trajectories that were going to go towards the nose to actually accommodate a Uranus flyby. Can't quite see the line behind our faces. And this scenario also, the current scenario is similar. We have 9 months to Jupiter, so really short in a solar system cruise. This was assuming launch from Earth 2030, but like I say, our current launch is 2040, and this scenario would fly past Quaoar in 2036 and ultimately get to 7 AU per year. So the scenarios we've seen this week are just over 7 AU a year. So we're in a similar option space, but we have decided on a trajectory. So I'll just remind you, just so that we're putting it to bed, we understand we're not going to get our ice giant flyby. This was also from last year. Our working group quantified what it would take for Uranus and Neptune, how far they were from the nose, whether that distance was increasing or decreasing during the window of time that we were considering. And I think, well, at that point, we hadn't totally ruled it out, but we were just defining the parameter space to pass back to the project. So now this week, we've seen the project have decided on not a final trajectory, not the final word on it, but they've chosen a parameter space, which is shown here. Lovely, but there's too much on the screen. So this is the study target. So this is a similar map to this one, but it's got a lot more information on it. So Elena has kindly offered to talk us through what you're looking at here. Is that okay, Elena?
Yeah, absolutely. I'm probably mostly just going to repeat what Wayne described this morning. So this is, of course, the very rich plot, and the color shows you the speed. You can see the color bar on the right show the speed in astronomical units per year. And so the way to read this plot is you pick the direction where you would like to go. So in this case, this is a study target. You see this white little dot here, and it puts you, it dictates the launch date. So if you go down here, you can't see very well, but it dictates the launch date, which means for this white dot, it's going to be late 30s. And the color gives you the speed that you can achieve, which is like 7.5, almost 8. I guess 7.5 AU per years. I think this is the way to read this plot. If you're interested in some other direction, I don't know, we can pick something interesting. Abby, which one? Something that catches your eye. For example, Uranus, right? So that means that it puts you to the launch date. Well, it should be here on the bottom, but it's not here. So, well, presumably, probably like 2033, 32. And the speed would be also, since it's in this red region, so it's going to be something between 7 and 8 astronomical units per year.
So you can't, still don't understand it.
What do you have a question?
Yeah, I think. So I would have thought you could launch, so this is Uranus from 2035 to 2044. So you could launch in any of those years and go past Uranus. Oh, I see. Right. So if we want to go past Uranus and we want to go past Uranus quickly, so in the middle of a red dot, then we go at 2033. And I remember, yeah, there was the white years were along the bottom when I first saw this.
Yes, I think that's the right way to think about that.
And then these are red in blobs.
These are blobs, and so as Ralph described this morning, these are the blobs that are coming from the Jupiter orbit period, which is almost, let's see, is that 10 years, something like that?
Yeah.
11 years. Yeah.
Right. Okay, yeah, 11.86 years, in fact. Yes, okay.
Yeah.
So every 11.86 years, Jupiter is back in the optimal position that when we go past it, we get as much speed as we could possibly get, which is why we want to pick one near the middle of the red.
Yes, that's right. Yeah.
All right, great. Thank you. Any questions?
And of course, this is the study target is the target that is chosen for the baseline mission that it's being studied right now by engineering team. So it's not picked, you know, it's just the choice for the baseline study.
Right. All right, does anyone want to ask any questions for clarification on that before I move on? That's important. All right. So some high-level questions that you've seen before, if you were at the last workshops on this, pertinent to exoplanets, is what does the solar system look like to our nearest extraterrestrial neighbours? Would extraterrestrials be capable of detecting life on Earth, and if so, what methods would they most likely use? I don't recall it, but there's a paper I read years ago based on, maybe it was a Galileo Earth flyby that said, could we detect life on Earth? What insights can we gain about exoplanetary systems by observing our own system up to 1,000 AU, which applies both to exoplanets and to their host stars? So those are the bullet points that Kevin Stevenson shared at the workshop in New York last year. When we were all together in New York, fancy pantsing around. It was great. I missed that. So what I thought would be a realistic thing that maybe could be achieved from a heliophysics payload with a simple camera would be creating the movie of the solar system. So maybe once every month, we add a camera, but then we use the camera to look back and just look at where the planets are, and then we do that every month, and eventually we create the movie of all the planets going around the sun, and hopefully we get some spectra from the planets that can give us some information on, you know, we know the ground truth of what that planet really looks like, and then how would we interpret the spectra in order to get close to what we know that ground truth would be. So it gives you some error bars that the exoplanet community could use. Seems a vital, simple thing that we can provide. So this is a plot from Sonny Harman's white paper to the Planetary Decadal Survey. Shows you the angular size in arc seconds of the different planetary bodies. This is, for example, this is where we do the Jupiter flyby, so Jupiter is really big. And then this is the angular separation between the sun and the planet as we move out in distance with the Interstellar Probe in units of astronomical units. We also discussed last year if we had any plausible opportunities to do images of transits of planets, and that was ruled out because of the sophisticated instrumentation that we'd need to do something like that. So we're looking at the most simple camera that we can to make some sort of observations of these planets from a distance as we go out. I'll also note that, well, I'll show you in a minute the current payload, but the Aurora is something that I've been talking to the exoplanet people about, or hopefully they've been listening, but I've been talking about for a little while, which is there's a lot of models now for exoplanets that deal with clouds, and cloud cover is really vital to understand, to really understand the differences between seeing the surface of a planet and seeing the consequences of clouds. And so what they haven't considered, what hasn't been included in any studies that I've seen so far is what the effect of an aurora might be on observations of exoplanets. So it's something that I think would be powerful to understand, just to offer it to the statistical surveys they're doing. But I also think that once we, maybe after James Webb is up, we might be able to use the auroral footprints, or some systematic change in the aurora that has a rotation rate that's not the same as the planet, that's not associated with the star. That rotation rate is probably going to be due to an auroral emission from a moon that's circulating that giant planet. And if, as we're continuing to explore in our own solar system, we start to think, well, maybe the most likely places to look for life off Earth in our solar system is in the oceans of the moons around our giant planets. And certainly we are finding giant planets around giant exoplanets more easily than we find terrestrial planets. So this just might be a really nice route of research, which would be a rich route of research that is available to us as planetary scientists that we could bring to that community, which currently really isn't studied at all. Then we also have the Hypothetical Planet X, which we discussed in quite a lot of detail last year. At the time, we were thinking, well, if Planet X was discovered and we could identify where it was, that our mission would turn into a Planet X flyby mission. And I don't know, I guess that the idea that there's plenty of rogue planets out there, that there's other objects beyond our solar system, there's plenty of dwarf planets, we start to wonder if that would indeed be the case. But certainly, we've got to keep it on the table that would we, and therefore should we, make sure that any payload that is launched on an interstellar probe is equipped and ready to take observations of Planet X if we find it exists. So summary musings, and we'll move on to the options in a second. Interstellar Probe could provide a great platform for exoplanetary science and for understanding our solar system as a habitable astrosphere. Look back at our solar system in exoplanetary context, recreate the pale blue dot, which I love, the idea of that. The search for habitability in all the different forms, knowing what we know about our own solar system and putting that in context with exoplanets, and create a real movie of the solar system. And the movie that's playing at the bottom was created from Galileo's sketches of the Jovian system in the 1600s. All right, so just to advertise, we've been busy talking about these things to the Planetary Decadal Survey, and I think there's also papers advocating for such measurements in the Astrophysics Survey. This is a paper by Sunny Harman, who also elucidates on the opportunities to make these, or remake the pale blue dot observations. And Candy Hansen, who's online now, and now I know more about this, is that Earth was in a sunbeam. So this is a common effect on the Voyager camera. And so when Candy first looked at it, she thought, oh, we've missed it. And then there it was hiding in one of these artifacts. And it's right in the middle. It's really quite chilling. All right, so here's the Helio payload. Maybe we'll come back to this. Crucially, apart from the Lyman Alpha, which I guess is a sort of an ultraviolet camera, there certainly isn't a visible of what we recognize as a camera on the baseline heliophysics payload, as you might expect. So this is a slide from Kirby's working group yesterday for the planetary, which was cameras on spinners are hard. We talked about the Juno camera, and we talked about New Horizons. What we came up with. So this is the spacecraft concept summary. And then I'll show you what are the options? How could we accommodate a camera? So Alan Stern had the idea of adding a CubeSat, which would dock, would de-dock, undock from the spacecraft, and then it would not be rotating, and the spacecraft would carry on through, and then it would dock. So it would make its observations of the KBO, and then it would dock back on. Equivalently, it could undock and make stabilized observations of the solar system and then dock back onto the spacecraft. And then perhaps what is maybe more realistic, or it's hard to imagine where we would put a rear view camera, but is cameras actually mounted on the rotating spacecraft platform. The one that would get you the biggest field of view obviously would be something along the axis perpendicular to the spin axis, so you would be just rotating all the time. And could we make sense of images like that? So as we're going out in the solar system, maybe the high gain antenna could be oriented perpendicular to the Earth, or when the Earth is far away from the sun. Hard to imagine how that would work. But we can make observations from the rotating camera. And I think that that's similar to how Juno can collects its images, but that's why I invited Candy to join to discuss. Then the other options would be to put a rear view camera back here, which I gather is a popular piece of real estate on a particular current design. And then the hopeful thing for a rear view camera, literally just staring back at the solar system in the, I think, nominal design would have to have it posted in the middle of the high gain antenna, because that would nominally always be Earth pointing. All right, so let me open that up for questions and discussion. I've lost you guys.
Abby, I have a question, if I may.
Yes, yeah.
So could you talk a little bit more about what kind of camera you mean when you say camera to take an image of the solar system?
Well, the Juno cam just gets you one image. I think it would be nice to have something that was more of a spectrometer, but in visible wavelength, VisIR, like the New Horizons. Is Kirby on? Kirby, what did you have for your? I think it's just this.
Yeah.
It would be the same camera that we'd have for the planetary payload.
Well, yeah. So, who was speaking?
Go ahead, Kirby.
Oh, go ahead, Kirby. Go ahead.
Well, so for the true planetary camera, it would probably be something strongly inspired by the Ralph New Horizons camera, both the MVic and the LISA components of that, in terms of the pixel field of view, which is about 20 microradians, and the overall field of view, which is about 5.7 degrees. For a look-back camera, if you're okay with
that
not,
again, Kirby?
What's that, Abby?
Just say that again. Lucy, MVic.
Yeah, so MVic and LISA are the two components of the Ralph camera on New Horizons, and the pixel size is 20 microradians is what it is for the MVic, which is the visible and very near infrared. Let's see. If you're okay with not resolving the planets and you just want to get photometric and spectroscopic, or maybe not even spectroscopic, but multispectral images of them, you could envision like a wide angle camera, like tens of degrees, similar to like the SIVA cameras on the Rosetta spacecraft. And you could even imagine like a Bayer pattern on the CMOS or CCD detector, where you do like a Bayer pattern, like what's used in commercial cameras to give 3-color view, except you could cheat and you can actually get it with 4 colors. And you could start getting multispectral and images of unresolved solar system planets at different phase angles that would be analogous to unresolved images of exoplanets. And by then kind of doing the inverse problem, you could look at the photometric and the phase rotation curve images of solar system planets, and you could invert the problem and infer, and you could back calculate out what possibly the winds are doing, how the planet's illuminated, different things like that, especially if you had Earth-based observations of the planets at the same time. So for like Jupiter or Saturn, I mean, for all the giant planets, for all 4, you could invert the problem, and then you could take that algorithm and start maybe saying something more useful about what's happening on exoplanets based on their unresolved disks. But like a rear view camera could be relatively simple. Yeah, the SIVA, CIVA cameras.
What you said, what did you mean, like full wavelength?
Yeah, so
is that IR as well?
I got a suggestion, Kirby. I know you've done some thinking about this. Do you want to maybe capture some of that, write it into the chat so we can just pull it right off of there?
Okay.
But I'm also curious for all of you who are listening in, what kind of science would you want to get off of a camera like this?
This is Casey. I'm going to help answer that. You want?
Yeah, go ahead.
Yeah, the MVic camera on New Horizons, just for a piece of information, is a 4-color camera, 3 optical, and 1 very near infrared called the methane channel. So it gets out to about 1.1 microns. Typical exoplanet studies nowadays, light curves and phase curves, are usually done with spectrophotometry with a few color bands and I'd say about 10 total bands, 3 or 4 in the optical, and the others going out to like 2 microns in the near infrared. And they're looking for things like methane and water and CO2.
But Casey, you have to remember that the targets that they're looking at aren't anything like most of the solar system planets, right? So that there's a heavy bias towards hot Jupiters, for example, and doing phase curves for things that are very, very much warmer and more giant planet-esque than the things that we could potentially look back at with solar system the terrestrials, for example.
Most of that is driven by current technology because the hot Jupiters, remember, they're the easiest things to see, right? They're hot, they're big and bright. And those were the first ones found, and everybody thought there were hot Jupiters everywhere. Now we know they're just a few % of all systems. But my argument is that if we're talking about a 50-year mission that's going to start in 2030, I think you should go ahead and plan ahead a little bit and go ahead and try and do not just the Jupiters, the Jovian planets, but go ahead and do the ice giants and the terrestrial planets, because technology is probably going to catch up in the exosystem. But I'm also just saying what is currently being done. And a lot of the work isn't just simply getting 3-color light curves in the optical. It's actually trying to figure out what is going on with these planets' atmospheres.
Is methane one of the light curves in the optical? Sorry for not knowing.
I'm sorry?
Is methane a light curve in the optical?
Methane's typically done, there's a few bands of methane, typically done in the very near infrared, 1 to 2 microns.
Oh, okay.
Want to look up a brown dwarf spectrum? You know it from Jupiter, probably, in Uranus. The same methane bands you're used to working with.
Yeah, I'm just pretending to be done for the conversation.
One question I've had all along on this, and I keep forgetting to ask it, is do we need to occult the sun?
No, we talked about that last year. Yeah. Sorry, go ahead, Sunny.
Oh, I was literally going to say the same thing that you said, Abby. We talked about this last year, and packing a solar occulter into a tiny little rear view camera is a large technical challenge that I think if we're talking about saving space and engineering overhead is likely outside the purview of an instrument like this. So when we talked about it specifically, like Michael Zemkoff and Casey and a few others were talking about it, it seemed more likely that if we are relying on the spacecraft spin, we can actually have that do work for us by just having the camera actually mounted slightly off axis, or pointing slightly off axis, and so it just naturally avoids looking back at the sun. And if we are fighting for real estate at the rear of the spacecraft, then offsetting that from the central axis makes the geometry slightly more complicated, because then you have to choose sort of when you lose specific planets from your view, but it's not insurmountably difficult to imagine that even if we're not on axis, we can still make the same kinds of observations.
Thank you. That sounds a lot simpler.
It doesn't quite get to the nub of what science can we really do. But I think as long as we're communicating this adequately, because people will say, you can take a picture of Jupiter or Saturn from the Earth and you can turn it into a pixel, and people have done it for the Earth, and then you will know what that looks like through a telescope. You could just model it from an observation that has more pixels, or you could just make an observation that just had the 1 pixel. So our argument for moving out in the solar system and looking back is kind of easily dismissed from people who say that, and our argument back is you don't know that until you've done it, which is not the strongest argument in the world. So I would like comments on that. I mean, what is real science?
May I borrow the screen and I can answer that while I'm doing that? I want to show you a spectrum real fast, spectrophotometry.
You want to share?
I'm sorry, I'm talking over somebody. I'll go real fast, just so, thank you. The point I'd like to make is that you can never get phase curves from the phase angles that we're looking at with ISP, looking back towards the star, and that's exactly what we'd see when we look at other exoplanets. Kirby was exactly right. We can get unique phase curves. So if you guys can see my screen, here's an example. Abby, you're gonna like this. This is I think it's 76b. This is actually a Neptune-sized exoplanet. And here is the spectrophotometry that people are now, this is state of the art with Hubble. And you see each one of these little discrete points. They're going after water here. They're going to methane at very long wavelengths and CO2. I thought there was also methane in here. But this is an example of how one would use spectrophotometry to characterize an exoplanet and also maybe our planet. You want to get a lot of little discrete points. There's a few visible and a lot in the near infrared. And these are the typical wiggles you'd expect to see in your exoplanet or emission peaks. So I hope that was useful.
Yeah, absolutely. So the phase curves, that's a vital point. We can't, and we'll have a great vantage point to see them as they're going around the sun.
Kevin, of course, knows this by heart.
Who was trying to speak when Casey started speaking?
Sorry, that was me, Sonny Harmon. So I was suggesting that there's a couple of things that we highlighted in the white paper, right? That the look back buys you, right? So the full phase curves are something that we can't get from Earth, like Kirby mentioned, or like Casey mentioned before, right? They're difficult to see because you're limited by where you're observing from, and in terms of variability as well, like we're talking about being able to view planets evolving through time over the course of decades, which is something that, especially when we're concerned about how exoplanet systems evolve over the course of days or weeks, like that could be an issue where these sort of long duration observations could help with answering some of those questions about how much you have to care about variability for particular planet types. And then there's also the practical aspects of actually observing exoplanet systems with things like zodiacal dust contamination or background light sources, like how you disentangle them in a practical sense. And especially since we've sort of gravitated towards the idea of, doing these aggregated images where you've got basically the camera or the spectrometer is spinning around the central axis and just accumulating some annulus of sky over a certain period and deconvolving that back on Earth. Like that's, like Casey mentioned, a direct analog to exoplanet observations. A good analog, I should say. It's not a direct analog because it's not quite the same physical orientation, but it's very much in the same, it's in the heart of that problem. And I think that, what's that?
Did you put a similar white paper into the Astrophysics Division survey?
I don't think I put one into the astrophysics. I think, didn't Michael Zemkov put in one to the astrophysics survey that was tangentially related to sort of lookbacks and doing science like this? I'd have to double check. But the other thing I wanted to get at was Michael's first question about what we actually want. I'm sorry?
Sorry, carry on.
What we would actually want from a planetary science perspective is, right now we're sort of attempting to bend the arc of spectral resolution to things that we can get in the next generation of space telescopes. So for terrestrial type or mini Neptunes, we're thinking about spectral resolution on the order of R of 100. So not just 4 colors, but actually getting spectrally resolved images of planetary systems. And I think that we certainly could take something that's not an EPO camera and actually elevate it to do practical science. But I think that if I can borrow from the latest parlance, like the stretch goal here is that we actually get something that can do the science that we want to do with not just the current generation of space telescopes for hot planets, like you saw, that there's only 2 bands for IRAC for the IR stuff. Like we want to get more spectrally resolved features than that in preparation for doing things like James Webb's observations of exoplanet systems. So R of 100 is a really fantastic goal. If it's not practical, yes, I recognize that there are space and power and data restrictions, but that's where I would like to see this get to. But
what does R of 100 mean?
That over a particular spectral range, so let's say 0.7 or 0.4 to 1.2 microns, you're getting approximately 100 data points.
As opposed to 4?
As opposed to 4, yes.
You with SIVA.
Yeah.
Okay. All right. So hopefully that's persuaded you that we have the arguments in hand and written up in white papers. So now we want to think about how we might accommodate such a thing on our current version of Interstellar Probe. So, well, I suppose, to augment or to argue for augmenting a camera like Kirby's described to get 100 data points per spectral window. Do you have any feelings, Sunny, or anyone for the weight of that camera, of such a camera?
I'm a theory guy. I'm sure that if Michael or Casey probably know or have a better idea, but they do actual like observations and build instruments and stuff. I don't do that.
If you want some context, the spectrophotometry I just showed, that Neptune X-size exoplanet, that was R about 20. I just did a quick calculation.
Have we got an example of a planetary telescope that's got 100 data points in that window and what the weight and power is?
This is about R20. Oh, and this was done from Hubble. So that's not a small instrument.
Right. You don't need Hubble to take pictures inside the solar system.
Nope, that's exactly correct. Very good point. That's the advantage.
That would be nice. But
No, that's exactly, that's actually the point you make. That's a very good, simple
that's
point.
the point, right? But what does that camera look like? Is the Cassini camera like that? Is the ice on Clipper like that? How can we not know that? All right, that's homework.
We know that Lori on New Horizons is about 12 kilograms, if I remember. And that's a low light camera. You probably don't need all of its capabilities to do it.
Well, let's talk about that then, the placement. So if we wanted to have 3 such cameras, maybe I'll share mine. Well, I don't like sharing because then I can't see the chat. But obviously it's vital that you see this, this little sketch. So at the moment we're talking about having a camera on the, what I think is normally the ram facing side of the spacecraft. We're talking about having one on the rotating axis of the spacecraft, and we're talking about having one as a rear view camera. So I see on this CAD drawing, we have a little platform sticking out here. Can anyone tell me what that's for? And if it has a friend on the other side? Are there many of these?
I believe that's the magnetometer. The longer booms are the antennas for the wave instrument, right?
Abby, that short thing you're pointing to is the ENA camera.
Ah.
Say that again, Kurt.
That's the ENA camera for looking at the heliosphere.
Huh. So on our Neptune concept, we did put the ENA camera on a little platform along with a lot of other cameras.
Abby, do you want me to talk about JHUAPL?
That would be wonderful. Thank you.
Okay. Let me share my screen here.
Yes, sorry, Candy. I didn't realize time was ticking away so much.
Yeah, sorry. Hold on a second. Okay, can you see this?
Yeah.
Yes.
Okay. So JHUAPL is about 6 kilos, just for reference. It's a push frame imager on a spinning spacecraft. Juno rotates at about 2 RPM. And so rather than fighting the spacecraft motion, we use it to do time delayed integration. And so we've got 4 filters. They're mounted directly on the CCD. Not that you have to use a CCD anymore, but that was the technology of the time. And so as the spacecraft spins, charge is transferred in a push frame mode that allows us to build up the integration. And so it builds up our signal to noise. So rather than fighting the spacecraft spin, we use it. Now, we are pointed perpendicular to the spin so that as the spacecraft is spinning, the filters are moving across the body. I don't know if you can see my cursor. So
Yeah,
you'd have to mount it in such a way that, you know, that this is possible. But we've gotten beautiful images with this camera, and it was not expensive and not big. We do have, for the purpose of imaging Jupiter, we have a 58-degree wide field of view. You could, you know, put other optics on, you know, kind of as you wish. And the other thing, if I can do this, is that we got a movie sort of similar to what you are talking about, Abby. And forgive me for, I'll have to, I guess, just talk over this. Can you still hear me?
Yes, you can.
Okay. So this was our on approach to Jupiter. We actually took images about every 15 minutes, and it basically in honor of Galileo. And I love the little sketch movie that you have, Abby. I want that.
Isn't that great?
Because that is what, this was us honoring Galileo. We took pictures of Jupiter and the Galilean moons as we approached, like I said, about every 15 minutes or so. And our plan was to do it long enough to catch one full orbit of Callisto. And so you can see Callisto out here. It's not very bright. It kind of blinks in and out. But this, I think, is quite similar to what you're envisioning.
Exactly.
Another cool thing is watch the satellites disappear when they go through the shadow. So you can see them going through the shadow and then, coming back out in front. And Io, of course, going around the fastest. So anyway, and then, of course, the beautiful music is from Vangelis.
Oh, is that right?
If you want me to stop, I can, or we can just let it finish and you can just enjoy it.
Let's get in there now. Great, so that was the first time.
Yeah.
Researchers did their job, right? That really is the first time that movie was made. Oh, bravo.
That's really cool. Thank you for sharing, Candy.
Yeah.
So some of the discussions we've had in the past are this product is like, this is what we want, right? And so the timing would be different, of course, because Jupiter takes so many years to go around the sun.
Yeah.
But we're going to fly by Jupiter less than a year after launch, right? And so looking back towards the center of the solar system for the next 49 years, Jupiter is only going to move around the sun a couple of times. And the inner planets are going to disappear into the noise of the sun's brightness itself after not too long. And so how do we reimagine JunoCam to be the camera that could pick up that kind of light? Because, I mean, you were able to take this when you got close enough to Jupiter to see more than just a, part of a pixel per Galilean moon, right?
Yeah, that's where the optics comes in. Like I said, we have a 58-degree wide field of view, and that's based on Jupiter. And so, yeah, these moons were sub-pixel up until the very end. But you don't have to have those optics. You could choose something else. Or you could choose a detector. Ours is 1,600 pixels. If you had, I don't know, a 4,000 pixel across detector, there's things about the design that could easily be changed. I think my main point was, was just because your spacecraft is spinning, that's not the end of the world for an imaging system. You can use it to your advantage.
Because you took this off of spinning Juno.
Oh yeah.
Yeah. I think Abby's vision for this is fantastic, to take and create the power of what you've got here for Interstellar Probe. That's right where we want to be. I mean, this is so cool.
I will also point out that there is something to be learned from the phase function. We did not actually expect Callisto to be so dark. That was our, little bit of lack of understanding of this is 90 degrees and how bright Callisto would be at 90 degrees. That's amplified, of course, multifold for the outer planets. The only phase function data we have at all on Uranus and Neptune is from Voyager.
That's a great thing to know.
I have a quick question. This also came up yesterday during Kirby's talk. Does Juno have to do any sort of fancy deconvolution to try to remove the effects of rotational smear on your imaging, or
No,
is it just got big pixels and the smear isn't important?
Right. Well, no, we shorten our exposure time so that it doesn't get smeared. But the time delayed integration means that you're transferring the charge also. And so in the end, we don't have to worry about smear because the exposure's short. But to build up integration, we transfer it from one set of rows to the next. It's called a push frame imager, or you could use a push broom. That works the same way, pretty much.
So you're smart about clocking it and you have short integration time. Got it.
Uh-huh. Yeah.
And it's 2 RPM, which is in the ballpark for what we're talking about with ISP. Okay.
Okay.
2 RPM, I think we're talking closer, we're like at 5+, but
We are? I thought we
because
were
of the
1.5.
long booms that we have, the wire antennas require a higher spin rate. Yeah.
Okay.
Well, I mean, you'd have to do the math, but I think it's a design worth looking at.
And actually, Candy, quick question: is this video available online? My kids have been looking at exactly this through binoculars off of our front porch because Jupiter has been so visible. They'd love to see this.
Yeah, it's on our website, Mission Juno. I'm actually, honestly, not quite sure where it is these days. It's probably buried in the press release from July in 2016. So if you can't find it by just poking around, let me know, and I'll see, if I can point you to it. But the cool thing,
Google remembers these things, so
yeah, or that, just Google it. So
anyone wrote up the science paper on the Callisto being darker, because that would be a nice one for us to reference about the.
No, it wasn't that big of a deal. It was just like, okay, the phase function.
Well, don't tell people that.
It wasn't worth writing a whole science paper.
Well, thank you so much for sharing this. It's awesome. Love that.
Oh, and the other point I wanted to make about this is you actually cannot do this from the Earth because pretty soon the sun comes up. And so your movie would have big, 8-hour outages.
Oh, yeah.
And so we had to do it from a spacecraft. And it makes it all the more remarkable that Galileo was able to figure things out the way he did.
Yeah. Yeah.
Cool.
All right. So hopefully we're persuaded. Well, I don't know, actually. So we should think about using a JunoCam type camera again. I hadn't actually appreciated that we had. Andy, do you want to stop sharing?
Oh, yeah. Sorry.
I didn't actually appreciate that JunoCam had multiple wavelengths. Because I do know that somebody mentioned, I think, on the Neptune mission that we didn't want to do a JunoCam because it only had one wavelength. I don't know what they were.
Well, that would have been incorrect then, because we have. Well, so we went because it's an EPO camera. Although it turns out it can do really great science. We're doing great science on Jupiter. We went for RGB filters because we felt that would be the easiest for the public to work with, and to do their own processing. And then we added the methane filter for scientific reasons, to be able to do the relative cloud altitudes in Jupiter's atmosphere. You guys might want to choose a set of filters that's more in line with the astronomy community, and not straight RGB.
What wavelength is your methane filter?
890.
Mm-hmm.
Okay, I've got a silly question, but why not have this same wide field of view for our Interstellar Probe camera?
Oh, you could. I mean, it would be good for doing the solar system, but it would not be as good for your close flybys, because you'd have to get really close to them then. I mean, that's why the Jupiter images are so beautiful, is because we get really close to Jupiter.
So here's the solution, and perhaps is we have the ram-facing camera, or the side camera is the Kirby planetary camera, and then a camera, assuming this ENA thing sticks out behind the high gain antenna, a camera mounted here, that's the JunoCam, and it's our rear view camera, and it's looking slightly off axis, like Sunny described, and it's rotating with 5 RPM.
Yeah,
I've asked
like that.
Yeah, I know I've asked this before from the operations point of view, but just to confirm, there's no way during cruise or there's no way ever that the spacecraft can reorient or would want to be reoriented. in this scenario. Is that true? Michael?
Well, let me just say that on Juno, when we reorient, which we do occasionally, we do it by just, you know, well, now I've lost the word I'm looking for. We can do it. You don't
do
really.
Spin axis, right?
That's it. Thank you. Precession. We precess the spacecraft, and it's slow, but you can do it.
Yeah.
And we have more severe limitations because for us, if we go off the sun, you know, of course, we're not getting as much power. And so we have to, the restrictions of the battery capacity, whereas you guys wouldn't have to worry about that so much. You would just be worried about losing your comm link.
After a short period of cruise, we would probably be doing precessions on a very long gap, occasional basis, simply to precess our spin axis back towards the center of the solar system.
Yeah.
I mean, once we get out there, you know, that bore sight of the main antenna is going to dictate our attitude.
Right.
And I mean, JunoCam's primary goal, if you will, is that close-up, amazing wide field view of the surface of Jupiter.
Yeah.
Right? That beautiful shot was like the reason to be.
Right.
And so one of the things I think about, Abby, when I think about this camera is that that our primary field of view, our primary view of this is going to be the sun at the center, and then planets that are you know, in the ecliptic, essentially off to the side. And so at the beginning we might catch Mercury, maybe Venus, Earth, and then Mars, and then Jupiter, and they'll all be in that same plane. And so if we're on a rotating spacecraft, we don't need like a full 50-degree wide field of view to see that as we spin around. If there's a way to time the images so that we're taking just a slice of that.
Exactly.
As we catch the planets in their motion around the sun in that ecliptic, and it won't be a perfect flat plate sort of ecliptic thing if we go a little bit out of plane, but still it'll be mostly, you know, a narrow image and not necessarily a big square 50-degree wide shot. The rest of that's going to be black all the time, no matter what we do.
Right, that's exactly what I was describing when I was thinking of doing the slices with the planetary type camera.
Yeah.
I think that having a larger field of view on the rear view camera is desirable, but I can't quite think why. So
now, as Kirby was talking about with the filters earlier, if we did have a wide field of view and a square CCD, 4,000 pixels or whatever, as the camera spins past the planets, say Jupiter itself, right? If we had filters across and took 3 pictures as Jupiter went through, we could get Jupiter located on each one of those filters, right? So that's like a really, I think, low budget way to get the filtering done and to have multiple, multiple. We'd have to take multiple images for each rotation, as for each set of imaging campaign pieces, right? But we could definitely.
I think that for the Jupiter observations, because it has been so comprehensively done from close up, we're probably going to get more interesting observations again, looking back at it, looking at it at different phase angles. But yeah, from the public interest point of view, which I hope that you don't get bored of me saying, but we really shouldn't underestimate. And we should be thinking about how to get the humanities departments involved, historians, photographers, you know. But just, I think like JunoCam has set a really good example of doing poets. Give a part of that 9-month cruise phase to poets, and just see what they come up with.
And Abby, you know, this whole idea actually speaks very strongly to the question that Glenn asked in the previous session, when he asked, what are those milestones? What milestones can Interstellar Probe create so that there's public engagement along the way? And so it's easy for all of us to say, well, launch, milestone, fly by Jupiter 8 months later because this thing's screaming so fast out of the solar system. That's a nice milestone. But then a year after that, you can release the first video of an entire Earth orbit around the sun, right? From Jupiter and beyond. And you'll see Mars move a bit, and you'll see Jupiter move a bit, but that itself could be just this public relations milestone of, hey, the first time anybody's like mapped Earth going around the sun on its own, right?
Right, and then when you see Mars move a bit, then you have a writer that comes up with, or a poet or an artist that comes up with the history of Mars. I don't know what they would come up with, but that would be the final, the most cutting edge version of our observations of Mars. And it's the stepping off point into our observations of Mars like planets around other stars. It's capturing the imagination, and it's not, and I think there's an arrogance on behalf of scientists where we think we can capture their imagination. We should just give it, and therefore give it, i.e. invite them onto our team as if the history department was another instrument. And I'm sure they have a ROSES equivalent call. We just need to identify where their sources of funding are and just give it to them and see what they come up with. Because I can, just like Janet did with the sociology, they will come up with something.
So how, I know that we've got at least a couple of early career folks on this meeting. Do we want to have them raise their hands and float to the top of the participants list and maybe ask them for their input on this topic?
Can I get everybody?
So, while they're floating off, I'm going to say my goodbyes.
Thank you very much,
so
Candy.
much. Thank
Great
you
to
so
see
much
you.
for inviting me.
Thank you for tuning in, Candy. Good to see you.
Okay, I'll see you later.
See you around.
Okay.
I would like to suggest something that I've quite enjoyed that Michael's done at the other meetings, which is to write in the chat how you're feeling right now about this mission. What's your mood, day 3 in? And just write one word in the chat, and maybe I'll turn it into a word cloud if I ever figure out how to do that. All right, nice to know.
We should document all this.
Chat does
all
get
these fantastic emotions that you can see in the chat. It could be nice, board maybe with this sort of emotions.
Right. Well, that's what I said. The word cloud. Yeah. You can do.
Oh yeah.
Which word came up most? I bet James can do that. He's the co-host.
Yeah, all the chat is being recorded.
All right. Well then, perhaps we will put some of our early career scientists, or at least solicit comment from you on what you're hearing. Any ideas or just feelings about it? You can put it in the chat if you don't want to unmute. But... See, I wouldn't have spoken when I was early career. I had to do a 2-minute presentation once. It was my first ever presentation. And I've never had a drink before a presentation, but I was that close and I was terrified. All right, what more can we talk about? So I might wrap this up at 3:30. I know we had officially till 3:40, but we don't need to drag it out. If we're ready to finish. I'm so sorry about my dog whining.
So, Abby, maybe I'll ask a question. So I was wondering if using camera that is planned for the planetary observations, can we do observation, images like Candy showed, approaching to objects? Can we use just planetary camera instead of just, trying to come up with another payload? I mean, another instrument. Would it be? Would planetary camera be sufficient for such kind of observations?
Right. So let me comment on that. So that was the only camera I thought we were going to have available to us. So we need to do another study or another conversation, not necessarily a study, if we're going to think about a wider field of view. But the reason that I was arguing for putting it on the rotation axis was for exactly that reason. And it's almost like we build up a push beam image like the Juno cam, but they have a big field of view. But we really need it because we would make one line image. Remember, the planets are moving really slowly. The clouds aren't changing that much, and we're rotating at 5 RPM. So we have a line image, and we just stare, and we make our line image maybe only once a month or something. No, hang on, we need to do it. Oh. I had a scenario where it worked and now I've lost it.
Well, I guess I thought when we talk about planetary augmentation, we talk about 3-axis stabilized.
Oh yeah, for the planetary augmentation, it would be a lot easier. Because then we would, I don't know, I'll have to think about this now. Would we have to rotate the spacecraft if we only had a really small field of view? I suppose maybe we would. Maybe we want the spacecraft to rotate. Any comments? Not quite.
What do you mean by we need to rotate it? For what?
If we only have a small field of view, we're looking back at the solar system, then not all of the planets are going to be within that field of view. So somehow we have to scan, or we have to go back.
Oh, okay, I see. Yeah, yeah, yeah. If we don't look back, but if we just like look at the object we approach, then we don't need to rotate, right? We just like Candy showed. She showed how the system changes as you approach it, right?
We could make those. Well, no, the Jupiter observations also exploited the fact it has that wide field of view. I think I'll have to get together with Kirby. I do think that when we first talked about this was a few months ago though, we did have a scenario where the two goals were the same, because we talked about having the identical camera on the RAM and on the rear view camera. Yeah, I'll have to think about that some more. I do think that having something like a Juno cam, if it could be accommodated on the same platform as the ENA camera, might be a really obvious solution. Or even 2 of them. She said 6 kilograms. Tiny.
Hey, quick question, Abby. Sorry, if you've already answered this, then please just say yes, we answered it. I see Michael's question in the chat. I wonder if we go beyond the heliosphere, will it be easier to see the atmosphere of an exoplanet? Could you? We
did look at that. Was our first scenario. It was actually carrying like almost not a Hubble, but something that was a really capable telescope or a capable radio antenna even. Beyond the solar system, but no, we couldn't get the sensitivity to look for exoplanets directly. Because
this spacecraft itself is so small.
Right, exactly.
Okay, thanks.
So one of the futures of observations of exoplanets, and we're already doing it with the very large baseline arrays for radio telescopes, is probably to put a radio interferometer, and you would probably put it on something just like this spacecraft to get a baseline that's the size of the solar system, and then you can get awesome resolution in the radio wavelengths of exoplanets. Well, that's what they did with the Event Horizon Telescope, the very long baseline microwave or millimeter wavelength observations to image the black hole. Is one of them in space, or are they both in space? No, they're all Earth-based, and they're all run off of like highly synced atomic clocks and have to collect so much data that they can't send it over the internet, so they've got this sneaker net of massive hard drives to bring the data back to the processing center in New Hampshire. Oh, wonderful. Well, maybe it may be the same team that are putting together this white papers going in on putting a radio antenna on the moon. So, that's the next. I'd be very surprised if they were separated from that effort. Yes. All right. Well, I've got homework. Thank you for the discussion. All right. I guess thanks everybody for joining today. This is the last session for today. Tomorrow morning, when we kick things off, Andrea Harmon is actually going to give a brief tutorial on getting into and then using, what the heck's the name of the software we're using yesterday? GatherTown, thank you. For those of you who haven't used it yet, it's a lot of fun. You get to walk around. You can make your avatar dance. Yes, I just want to figure out where I get my diamond sword, like it's Legend of Zelda, but I don't know. Anyway, have a great day, everybody. All right. And thank you. Yes, thanks for joining and showing interest in this perhaps most sci-fi element of our incredibly sci-fi mission. Take care out there. Cool. Good job, Abby.
Thank you very much, Abby.
Thanks. Bye.
Great job, Abby.